What if the end of the world wasn't fire or ice, but silence? No explosions, no collapse into a black hole, just a soft, fading glow in the dark. That's how most stars die. And that's the future waiting for our own Sunday stars. Like the sun aren't the wild rock stars of the cosmos. They're stable, quiet, and patient, fusing hydrogen into helium in their cores for billions of years. That fusion is what keeps them shining, a perfect balance between the inward pull of gravity and the outward push of energy. But all things must end. Eventually, the hydrogen fuel runs out. With no more fusion to push outward, gravity starts to win. The core begins to shrink. As it does, the outer layers of the star expand dramatically, transforming the once ordinary star into a red giant, so large it could swallow the orbits of Mercury, Venus, and maybe even Earth. From our planet's perspective, it would be a stunning and terrifying sight. The sun, now swollen and unstable, begins to lose its outer layers. They drift off into space, creating a glowing, ethereal cloud of gas called a planetary nebula. Not because it has anything to do with planets, but because early astronomers thought they looked like them. What's left behind in the heart of this expanding shell is something tiny and extraordinary. A white dwarf. It's no larger than Earth, but it contains about half the mass of the sun. So dense that a single teaspoon of its material would weigh tons. There's no more fusion going on. The white dwarf doesn't shine because it's burning anything. It glows simply because it's still hot, like a burned-out ember at the bottom of a fire pit. Over time, that ember cools. Slowly. Not over millions of years, but over trillions. White dwarfs are among the longest-lasting objects in the universe. They're so stable, so quiet, that not a single one has yet cooled into its final state. A black dwarf. That's because the universe simply isn't old enough yet. Someday, in the far future, long after the last galaxy has faded from view, white dwarfs will become cold, dark, and invisible. They'll still be out there, ancient cosmic fossils, the final remnants of once-living stars. Dead, but not destroyed. And this is how our sun will end. Not with a bang, but a whisper. A slow goodbye that will outlast the Earth, the solar system, and maybe even time itself. But while some stars die quietly, others go out in ways that shake the fabric of the universe. Imagine a single star detonating with the power of billions of suns. In less than a second, a flash so bright it can outshine an entire galaxy. This isn't science fiction. It's called a supernova, and it's one of the most violent, awe-inspiring events in the universe. But before the explosion, there's a long, slow burn. Not all stars end their lives quietly like our sun. Some are born massive, 8, 20, even 30 times more massive than the sun. These giants live fast and die young. While our sun enjoys a steady fusion of hydrogen for billions of years, massive stars race through their fuel, fusing heavier and heavier elements as they age. Hydrogen to helium, helium to carbon, then to oxygen, neon, silicon. Until finally, they reach iron. And that's the cosmic dead end. Fusing iron doesn't release energy, it absorbs it. So once the core fills with iron, fusion halts. And with that, the outward pressure that held the star up vanishes. Now gravity takes over. Instantly, the star's core collapses in on itself, falling inward at a quarter of the speed of light. Imagine something the size of our sun crushed into a ball the size of a city. In less than a second, as the core implodes, the outer layers, unaware of the catastrophe within, keep falling, until they slam into the core with unimaginable force. And then boom, a supernova. Not just an explosion, a cosmic detonation. In a single moment, the collapsing core rebounds and blows the star apart. The outer layers are blasted into space at tens of thousands of kilometers per second. The light from that explosion can outshine a galaxy for weeks. And the energy released? More than our sun will emit in its entire 10 billion-year lifetime. But a supernova is more than just a light show. It's a cosmic alchemy lab. In that brief, explosive furnace, heavier elements are forged: gold, uranium, platinum, elements that didn't exist before. Everything heavier than iron in your body, in earth, in the air, in your bones was made in a supernova. the oxygen you breathe, the calcium in your teeth, the iron in your blood, all born in the heart of a dying star. So yes, supernovae destroy, but they also create. They scatter stardust across the galaxy, enriching clouds of gas and dust that will form new stars, new planets, maybe even new life. In a very real sense, we owe our existence to these explosions. And what happens after the blast? That depends on what's left behind and how massive it is. If the core is just right, it becomes something incredibly dense. A neutron star. If it's even heavier, something far more mysterious takes shape. A black hole. But first, let's meet the collapsed hearts of dead stars. Imagine crushing Mount Everest into a sugar cube. Now imagine doing that to a star. That's how extreme a neutron star is. When a massive star dies in a supernova, the core doesn't always vanish into a black hole. Sometimes the collapse stops just short, balanced by one last force of nature. If the remaining core is between about 1.4 and 3 times the mass of our Sun, it becomes something truly bizarre. A neutron star. And what is a neutron star? It's what happens when matter itself breaks down. The crushing gravitational pressure forces electrons and protons to combine, forming pure neutrons. The atom, the basic building block of everything, is destroyed. What's left is a city-sized ball, just 20 kilometers wide, but more massive than the Sun. The result? A level of density that's hard to even imagine. Just 1 teaspoon of neutron star material would weigh over 1 billion tons, more than every car, truck, and skyscraper on Earth combined. And these aren't just heavy, they're active. Neutron stars often spin rapidly, sometimes hundreds of times per second. A speed so fast it's like Earth completing a full rotation every few milliseconds. These spinning neutron stars emit powerful beams of electromagnetic radiation, like a cosmic lighthouse. When one of those beams sweeps past Earth, we see a flash. That's what we call a pulsar. Pulsars are so precise they rival atomic clocks. Some have been used to measure gravitational waves and probe the deepest laws of physics. But the weirdness doesn't end there. Sometimes, 2 neutron stars collide. They spiral toward each other, orbiting at incredible speeds until finally, boom, they merge in a violent explosion called a kilonova. These events are so powerful, they can create gold, platinum, and other heavy elements, even more efficiently than supernovae. They also send ripples through spacetime, gravitational waves, which we can now detect here on Earth. In 2017, for the first time, we caught one in action. A neutron star merger that lit up telescopes and gravitational wave detectors around the world. We saw the explosion and heard the universe. Neutron stars sit on the edge of physical possibility. They're the ultimate test of how matter behaves under pressure, density, and magnetism. Some have magnetic fields so powerful they could erase your credit card from hundreds of thousands of kilometers away. We call those magnetars, the most magnetic objects in the known universe. But even these strange stellar remnants have their limits. Add just a little more mass, and even the degenerate neutron matter can't hold itself up. Then, the collapse continues, and what emerges is no longer a star at all. It's something from which nothing, not even light, can escape. We're heading now into the darkest territory of all, the realm of black holes. Some stars don't just die, they vanish. When a truly massive star, more than 30 times the mass of the Sun, reaches the end of its life, even the incredible density of a neutron star isn't enough to stop gravity's pull. The core collapses even further, infinitely further, and something terrifying is born. A black hole. A black hole is not just a very dense object. It's a region of space where the known laws of physics collapse. Gravity becomes so overwhelming that nothing, not even light, can escape. This makes it the ultimate cosmic trap. Once you cross a certain boundary, you're gone. Forever. That boundary is called the event horizon. It's not a physical surface, but more like a one-way door in space. Once something passes through, a spaceship, a planet, even a beam of light, it can never come back out. What lies at the center? A singularity, a point of zero volume and infinite density. We don't fully understand it. Our equations break down. Space and time themselves seem to unravel. It's where Einstein's general relativity collides with the quantum world, and neither side wins. And black holes don't just sit there. They change the very structure of space around them. Get close to one, and time itself begins to slow. To a distant observer, you'd appear to freeze near the event horizon. Light bends dramatically. Orbits twist in strange ways. The rules of reality bend. But not all black holes are the same. Some are just a few kilometers across, the collapsed cores of single stars. Others are supermassive, millions or billions of times more massive than the Sun. They sit at the centers of galaxies, including our own Milky Way. We used to think black holes were invisible, hidden forever behind their event horizons. But in 2019, that changed. A global network of telescopes, synchronized like one giant eye the size of Earth, captured the first-ever image of a black hole. It showed a glowing ring of hot gas swirling around a dark center, the silhouette of the event horizon itself, 55 million light-years away in the galaxy M87. For the first time, we didn't just theorize or simulate. We saw one. It was one of the most profound scientific moments of the century, a direct confirmation of Einstein's predictions. But there's still so much we don't know. What happens inside the event horizon? Do black holes evaporate over time, as Stephen Hawking predicted? Could they lead to wormholes, alternate universes, the fabric of space-time itself breaking apart? These are more than theoretical questions. Black holes are not rare. They're everywhere, lurking in galaxies, devouring stars, distorting time. That they're not just the end of stars. They're the edge of knowledge. And in them, we might one day find the key to uniting gravity and quantum physics, the two great, unfinished chapters of modern science. Because when a star dies as a black hole, it doesn't just leave behind a mystery. It becomes one.